post-quantum crypto primitive hardware IP designed by Industrial Systems Institute for Work Package 4 of SecOPERA's project. The device layer solution proposed in this Work Package 4 provides security assessment and security hardening modules related to different devices. Our crypto primitive hardware IP core library contributes to this layer relative to post-quantum security. One of the modules that is inside our IP is the Lithium's digital signature hardware accelerated IP. It was designed in a parametric way for all different modes of operation and for security of the lithium. Also, the security of this platform, the system architecture, is made parametric so it can be reused for different IP modules inside of this core library. So a few words of our algorithms of NTT, which is a basic part of the lithium's signature scheme, can be seen here. This is the algorithm of the lithium library. There is a traverse between different number of stages, between different number of inputs and stages L, and for each of them there is a processing element taking place. We transform these algorithms to the algorithm on the right, traversing all different number of stages, and for each stage we have a butterfly loop which is based on loops, parallel loops of the parameter B, the index calculation loop, the memory read loop on these index calculations, the operation loop which is based on the memory that was previously accessed in this loop, and the loop that writes back the calculations to the memory. Each of these loops we can see it's based on the parameter B, which is the number of parallel processing element executions. In our case, B equals to 2, but it can be other higher values too. Same logic applies on the inverse entity, exactly the same logic. So we have two modules, the entity, the inverse entity, and then we have the pointwise multiply and accumulate. This is the basic three building blocks of the algorithm. So for each, the input is the two inputs is the input in and the input mod. As we can see, their dimensions. For each of L times n input, we have L times of entity to transform this input to the entity domain, and then for each L times n, we have the pointwise multiply and accumulate. As we can see, the second input is k times L times n, so we have k times this operation of multiply and accumulate inverse entity and then buffering the outputs. So the final module of the entity and the matrix multiplication can be seen here, the resource utilization. This is the system architecture of our design based on the Vivado system architecture. The IP was designed on VT's HLS code and can be seen here. So this is the processor. The processor communicates with the DMA, and the DMA communicates with a module between two FIFOs, input FIFO and output FIFO to the module. So the module here could be easily removed and insert another IP module. And this is the kind of reusability I was talking about in the system architecture. This is the results for different ARM CPU frequencies. We can see that higher the security of the scheme is 5. We can see the results are getting the gain of the IP is getting higher. So in our future work we would like to take the entity algorithm, which is basically the same in the Kuiper's key encapsulation mechanism, which is a post-quantum algorithm, KEM post-quantum algorithm, and then have a suite, for different KEM and DS algorithms that can be used for the post-quantum in an IP library. Thank you very much.